fellow AI and ML practitioners tuning in to AI Paper Slop. Today we are looking at the Qwen-Image-2.0-RL technical report, published June 29, 2026.
Oh, this one is huge.
It really is. This paper basically solves the massive challenge of extending reinforcement learning from human feedback, RLHF, directly to diffusion models.
Right, which has been notoriously difficult.
Exactly. And they do this by completely ditching standard pairwise reward models for a pointwise vision language model, or VLM, scoring system.
Which changes everything about the optimization.
Yeah, and to prevent the training from just collapsing, they invent this hybrid CFG strategy. Plus, to wrap it all up, they use a novel on-policy distillation technique based on the Wasserstein 2 distance.
Basically crushing highly specialized text-to-image and editing models back into a single foundation model.
You got it. And the results are just huge. I mean, they hit a 57.84 on Qwen-Image-Bench and saw massive ELO jumps, like up 78 points in text-to-image and up 93 points in the image editing arenas.
Yeah, and to understand exactly why those numbers represent such a landmark moment for the technical community, you sort of have to look at the historical gap we've been fighting in visual generation.
Right, between math and actual human taste.
Precisely. I mean, the foundation of supervised training for diffusion and flow matching models is denoising score matching. Conceptually, it's simple. You take a clean image, gradually add static noise until it's mush, and then train a neural network to predict and subtract that noise.
Step by step.
Right. It's mathematically sound, and it forces the model to learn the underlying data distribution. But denoising score matching doesn't inherently understand compositional harmony.
No, it doesn't care if a human subject looks completely physically distorted.
Exactly. As long as the pixel statistics match the training data, the model is happy. So bridging that gap between a model that just removes static and a visually stunning model requires a perfectly calibrated RLHF pipeline.
Right, because if you want to align a model using RL, you first need a highly reliable mathematical representation of human preference.
Which brings us to the reward models.
Yeah, and if you look at the LLM space, the default has always been Bradley-Terry pairwise ranking, right? You generate two responses, a human says A is better than B, and your reward model learns to rank them.
But the Qwen-Image-2.0-RL team proves that pairwise ranking is, well, it's actually the absolute wrong approach for vision.
They proved it definitively, yeah. They rigorously tested two distinct VLM-based reward training paradigms.
The first being that standard pairwise approach, minimizing the ranking loss on pairs.
And the second was pointwise, basically instructing the VLM to regress to an absolute 1 to 5 Likert scale score. And they didn't just ask for a number, they used chain of thought reasoning.
That's the crucial part. The VLM had to explicitly output its step-by-step rationale against a fixed grading rubric before issuing the score.
And the pointwise model just vastly outperformed the pairwise one, like consistently better visual quality, finer textures, fewer artifacts.
It's funny because if you come from the LLM world, that feels entirely backwards.
I know, but think of it this way. Pairwise is basically a beauty pageant where you only get to know who won. Contestant A beats contestant B.
Right.
But what if both contestants tripped and fell completely off the stage? The model just learns that A's fall was, like, slightly less terrible than B's. It never learns what a successful walk down the runway actually looks like.
That is a great analogy. Pointwise, on the other hand, is a strict grading rubric. It evaluates the absolute magnitude of quality.
So if both images are broken, they both get a flat one.
Exactly. With high-quality generative models, you frequently get two images that both match the prompt and have no obvious distortions. At that point, you're evaluating subtle texture quality or lighting.
And a relative ranking just doesn't give a rich enough numerical gradient for the policy to understand why one texture is better.
Right. By forcing the VLM to use chain of thought for a discrete score, you give the RL algorithm a much more stable and precise target.
So once they settled on this pointwise system, they built a highly structured, layered logic system for text-to-image. First layer is the alignment reward, which is ruthless.
Oh, absolutely ruthless. It explicitly evaluates semantic correspondence, object counts, spatial relationships.
Right. If you ask for a red car and get a beautifully cinematic blue boat, the alignment reward just hard caps your score.
Which mimics human expectation perfectly. You don't get aesthetic points for ignoring the prompt. And only once that threshold is met does the aesthetic reward kick in.
Evaluating compositional balance, lighting, texture. And then there's the third layer specifically for human subjects, the portrait reward.
Which makes a lot of sense given our brains have dedicated hardware just for recognizing faces. Generic aesthetics aren't enough when you're fighting the uncanny valley.
Exactly. Our visual systems are hypersensitive to microscopic facial proportions. So this portrait reward targets attractiveness, skin realism, and explicitly checks for things like incorrect finger counts.
Or distorted limb anatomy, yeah. But applying this to image editing tasks is where it gets incredibly complicated.
Because editing is fundamentally different from raw generation. Your rewards have to evaluate instruction following. Did you replace the apple with an orange without breaking the background?
Core edits versus auxiliary edits. But the standout for editing was how they handled facial identity.
This is such a critical architectural decision. The team found that while VLMs are great at high-level semantic evaluation,
Like verifying the apple became an orange.
right, they actually have a severe blind spot for subtle identity shifts in human faces during an edit. If you change a subject's shirt, the VLM says, yep, shirt changed, still a human.
But it completely misses that the person's jawline shifted by 4%.
Or their eye spacing changed, yeah. So to solve this, they completely bypassed the VLM for this specific metric.
And implemented a dedicated model-based embedding-level identity preservation scorer.
Basically extracting facial embeddings from the source and edited images using a facial recognition network and computing the cosine similarity.
Providing this highly precise, mathematically continuous signal to ensure the face matches down to the pixel level.
But having this strict 1 to 5 grading rubric is useless if the model doesn't know how to mathematically update its weights without forgetting its pre-training. Which brings us to FlowGRPO.
Group Relative Policy Optimization, adapted for flow matching models.
Right. The policy generates a group of images, evaluates them with the rewards, and computes the advantages. Basically, how much better or worse each image is compared to the group average.
But because they're using multiple layered rewards, they use multi-reward advantage computation with per-prompt group normalization.
Wait, let's break down that per-prompt group normalization. My initial instinct would just be to add the alignment score, aesthetic score, and portrait score together. Why does summing them break the optimization?
Because different reward models have completely different absolute scales and variances. Say your alignment reward is super stable, but your aesthetic reward fluctuates wildly.
Ah, so if you sum them.
The dimension with the highest variance completely dominates the gradient update. It pulls the model aggressively toward aesthetics, ignoring alignment and identity.
That makes total sense. So by normalizing the scores within each prompt group, giving them a mean of 0 and standard dev of 1, you level the playing field.
Exactly. It makes the composite reward invariant to scale differences, forcing the engine to balance all conflicting constraints simultaneously.
Okay, so we've leveled the gradients, but optimizing that policy brings us to the classifier-free guidance, or CFG Dilemma.
Oh, this is famously a nightmare in RL training.
Just as a quick refresher, CFG is how diffusion models push generation toward a text prompt. It runs twice per step, once looking at the text, once looking at an unconditional prompt, and extrapolates away from the unconditional prediction.
Right. And they tested 3 strategies for CFG during RLHF. Strategy 1 was using CFG in both the rollout, the generation phase, and the training phase.
And the result was severe training instability and image collapse.
Complete collapse. Strategy 2 was no CFG at all in either stage. The model got better reward scores, but suffered massive catastrophic forgetting.
Right. It forgot its pre-trained world knowledge, forgot what celebrities looked like, which leaves strategy 3, the hybrid strategy, which they adopted.
You use CFG during rollout to get high-quality candidates, but you remove CFG entirely from the policy optimization objective during the backward pass.
I'm stuck on something here, though. If the model relies on CFG to generate a coherent image, why does including it in the backward pass cause the model to implode? What breaks?
It's fundamentally about competing gradients. When you include that extrapolation step in the RL objective, you're forcing the optimizer to jointly update weights for both the conditional and unconditional branches simultaneously, all based on a single scalar reward.
It's literally like trying to ride a bike while someone else is sitting on the handlebars aggressively steering in a completely different direction.
That's a perfect visualization. The unconditional branch gets penalized for features the conditional branch is responsible for, and vice versa. It causes massive numerical instability.
So dropping CFG from the training objective isolates the updates on the text condition representation.
And as a bonus, running only one forward pass during training drastically cuts VRAM and compute overhead.
Speaking of compute overhead, generating an image with flow matching requires an ODE solver. It takes around 40 distinct steps. If you run RL updates across all 40 steps, doesn't the model just reward hack?
It absolutely does. It finds some microscopic texture loophole to exploit the VLM, and visual quality degrades almost instantly.
So how do they prevent that?
Time-step sampling. Instead of computing gradients across the full 40 steps, they restrict the RL updates to high-noise time steps, specifically near t=1.
Because at t=1, it's mostly Gaussian noise. The model isn't deciding on brick textures, it's deciding the global layout and semantic strokes.
Exactly. It forces the model to improve fundamental layout and alignment, making it significantly harder to discover brittle, fine-grained texture hacks.
That's super clever. And on the engineering side, hitting massive remote VLM APIs for every image generated would normally bottleneck the GPUs.
Right, so they built an asynchronous reward pipeline. GPUs generate images, hand them to background threads to query the VLMs, and instantly start the next batch.
Hiding the network latency entirely. Plus, they use prompt variance filtering. They throw out prompts where the scores are universally high or universally low.
Which is an elegant way to save compute. You only spend FLOPs on data where the policy actually exhibits uncertainty. If there's high variance, there's a meaningful gradient to learn from.
So we've scaled RL, filtered prompts, trained our policies. Now we have two elite, highly specialized models, a text-to-image teacher and an editing teacher.
But for real-world deployment, you can't spin up two massive models. You have to smash them together without them forgetting their skills.
Which brings us to the distillation masterstroke. The intuitive approach is just mix RL training a single base model on all rewards simultaneously. But they tested it, and it failed.
Totally failed. Because of cross-task optimization conflicts, the aesthetic rewards of text-to-image and the pixel-perfect identity rewards of editing pull the gradients in opposite directions.
So you get identity drift and incomplete complex edits.
Exactly. So their solution is on-policy distillation, or OPD.
This is legitimately brilliant. You initialize a student model from the base weights. The student generates its own trajectory, starting from pure noise, stepping down entirely on its own, without CFG.
Right. And then, at each time step, it looks at what the task-appropriate teacher, which does use CFG, would have predicted for the velocity.
And updates its weights to match the teacher's velocity. It's like a student taking a drawing test, making their own messy pencil trajectory, and the expert teacher leans over to correct the angle of the pencil at every micro step.
And it's not just a heuristic. This trajectory-level velocity matching has deep theoretical backing. In LLMs, distillation is straightforward KL divergence on next token prediction because the space is discrete.
But in continuous diffusion, calculating KL divergence between continuous path measures is generally intractable.
Right. So the paper relies on a theorem from Benton et al. From 2023. They proved that minimizing this trajectory-level velocity approximation error is mathematically equivalent to minimizing the upper bound of the Wasserstein 2, or W2, distance between the generated output distributions.
The Wasserstein distance, that's basically the Earth mover's distance, right? The effort to shovel one probability distribution into the shape of another.
Exactly. By matching the velocity field along the student's own path, you rigorously bound the Earth mover's distance between the student's final images and the teacher's,
ensuring the continuous flows converge at the end, and practically managing three massive models: student, D2I teacher, editing teacher. They just use dynamic GPU loading.
Right. They only load the specific teacher required for that batch. The teachers get to be entirely selfish, specializing completely without compromise.
And the OPD acts as a pure knowledge transfer mechanism. Plus, baking the CFG directly into the student's base weights makes inference faster.
And the final evaluations absolutely justify all this engineering.
They really do. The unified Qwen-Image-2.0-RL model definitively beat the MixRL baseline. It hit an ELO rating of 1193 in text-to-image and 1349 in image editing.
We're talking massive gains in technical categories. Plus 93 in 3D modeling, plus 91 in photorealism.
Proving that trajectory-level velocity matching successfully unified these tasks without any cross-task degradation whatsoever.
It firmly establishes this entire pipeline as the definitive template for post-training flow matching models moving forward.
Which leaves you with a final thought to ponder. If trajectory-level velocity matching via on-policy distillation can perfectly unite mathematically contradictory visual tasks without degrading them, just by minimizing that W2 distance bound, what happens when you apply this framework across modalities? Could you initialize an ODE-based student model and have it simultaneously distill a video teacher, an audio teacher, and an RLHF text teacher all along its own self-generated multimodal trajectory? Could this W2 bound be the key to a truly universal foundation model without ever having to balance the nightmare of mixed reward gradients?